Hello students, in this video we'll see an example of how we use the Gauss Divergence Theorem. Let's suppose that we have the closed unit cylinder x squared plus y squared is equal to 1, capped with z equals 0 and z equals 1. Find the flux of the vector field v of x, y, z, which is going to be, we'll have a, let's do a x cubed, y cubed, and then z x y. Okay, so there's my vector field. And so what we're asked to find is we're asked to find the following integral. We're asked to find this, i.e., find the flux of this vector field. So that's going to be x cubed, y cubed, z times x times y dot d sigma. And for a closed surface S, which this cylinder is closed because we're capping it off, so our cylinder looks something like this. So we have the unit cylinder. There's the z-axis, the y, and the x. Here's the unit circle. So this is included in my surface, so I include the unit circle up here, and then I include the unit circle up here at a height of z equals 1, and I connect it with this cylinder. So the surface is not only the lateral side of the cylinder, but it's also the top and the bottom faces of that cylinder. Okay? And so I'm asked to compute this flux. And now by the Gauss theorem, so by the Gauss Divergence Theorem, so this is by the Gauss Divergence Theorem, this is equal to the triple integral over the interior of the surface S of the divergence of this vector field of x cubed, y cubed, x, y, z, d volume. That's the Gauss Divergence Theorem. It says if you're finding the flux of a vector field over a closed surface, it's equal to the triple integral over the interior of that surface of the divergence of the vector field. So let's compute the divergence. I'm just going to write interior for the time being, interior of S. Then I'm going to have a 3x squared plus 3y squared, and then I'm going to have a plus x times y. Then we're going to have a dv, so in other words, we have a dx, dy, dz, so dx, dy, dz. But I'm going to immediately put this into cylindrical coordinates. Makes sense. I'm finding the volume integral over a cylinder, so in cylindrical coordinates, what do we have? Well, in this region, what can we say? We can say that theta goes between 0 and 2 pi. The radius goes between 0 and 1. And the z value goes between 0 and 1 as well. In other words, the cylinder in cylindrical coordinates is just a box. So what we'll have over here is we're going to integrate this from 0 to 2 pi for theta, 0 to 1 for r, and 0 to 1 for z. Then we'll have a what? Then this 3 times x squared plus y squared is really 3 times r squared. And this thing over here is going to be an r squared times cosine theta times sine theta. So we're going to have a 3r squared plus r squared cosine theta sine theta. And then we need to put in the Jacobian, which is r dz dr d theta. So now the z integral, there's no z's in here, so the z integral is just going to go away. We're going to integrate, because I'm integrating from 0 to 1, so that has a length of 1. Integral from 0 to 2 pi, integral from 0 to 1 of, let's multiply this through, I'm going to have a 3r cubed, and then a r cubed cosine theta sine theta, dr d theta. Now, when we do the theta integration, we can box separate this as well. When I do the theta integration, I'm going to be the derivative of sine is cosine, so this will be sine squared over 2 from 0 to 2 pi. Those terms will cancel out when I put in the boundary limit, so these average out to 0. And we can easily see that because the average value of x times y in this cylinder, it's a symmetric region, which includes both positive and negative values. So the first and third quadrant and the second and fourth quadrant terms will cancel each other out. And so what we have over here is we just have this integral to do. So we're going to get a total of what? for my theta integral, there's no thetas over here, so I'll just get a 2 pi for my theta integration. And then I'm going to have a 3r cubed. That's going to integrate to 3 over 4 r to the 4th from 0 to 1. So that's just going to be a 3/4. So I'll have a 3 pi over 2 as the flux of this vector field over the surface. So we saw that instead of having to actually parameterize the 3 parts of this surface, find the normal vector, parameterize the surface, and then plug it in to this vector field, it was much easier to use the Gauss theorem because it simplified things. It went to a higher dimensional setting, but I did a derivative of the vector field, which simplified the calculation. Thank you very much.